Okay, 6 o'clock. Let's get started. So this week, today, and uh, like a next day, we'll be doing a review for the midterm, and that's where there is one discussion topic specific generated for you, which tells about details about the midterm. I hope you guys have gone through that one, and I already see some of the topics of interest has came up on that part, and I will go first with those things. Okay, let me see. Let me share my screen. Okay, so as general information, let me just, if you have not didn't get a chance to look into these discussion topics and the announcement or other sources, like this is more general information about your midterm review topics. It includes from lecture 1 to 12, module 1-4, and you are allowed one A4 size cheat sheet. Both sides is allowed. You can use your own blank scratch paper to solve the problem. You can use calculator, including the programmer's calculator, which uses this hexadecimal, all these part, right? So you can do that. And also, okay, there will be some essay questions and which needs proper explanation. And if you need, you use all the features in the text editor in the Canvas quizzing environment to boldface, underline, and all this stuff for easy reading of the answer. So that's very important. There are total 75 minutes, single attempt. And I'll be present through the Zoom session in your regular class. Like in the same time, I'll start that Zoom session. You don't need to log into that, but if you have a question, then what you can do, you can dial in through the phone. So make sure you have the required dial-in information from your registration email from Zoom. So you registered for this class in the Zoom session, and then that registration system sent you some detailed information about meeting IDs and all this link. In that email, you will specifically find the call-in information where you can actually dial into an 800 number or so, and dial in some meeting IDs or whatnot, and then you will be connected through the audio into the Zoom session so that you can ask me specific question. Is that clear for everyone? I hope so. Next one is, as I said, exam will be 75 minutes long, and it will be available from 5:50 p.m. That means you can start as early as 5:50 p.m. You don't need to wait till 6. It will be taken through the Respondus lockdown browser and webcam, just like the quizzes we take. Exams will be automatically submitted at 7:20 p.m. So we have kind of a 5-minute buffer gap after the class time, but you will still get 75 minutes. It is not that you will get entire time from 5:50 to 7:20. So those buffer time, 10 minutes early and 5 minutes late is for, let's say you have some technical problem, maybe 2-minute delay, 5-minute delay, to over offshoot those kind of timings. But I would say start early, start at 5:50 p.m. So that you make sure you get all 75 minutes you need it, right? Exam will be automatically submitted 7:20 means if you, let's say you are late at 6:15, then you are actually already lost some minute there, right? So make sure you start early at 5:50 p.m. sharp and start taking the exam. There will be 35 pop quiz and quiz style questions, total 55 points. Kind of breakdown of about 21 pointer, multiple choice, 10 2-pointers about multiple choice, tiny problem, like some problem that you can do through the mental calculation. You should be able to do some mental calculation, that kind of problem. 5 3-pointer small problem, it is more like in your detailed understanding, and it's a quicker problem. You don't need to think much about those problems if you have prepared properly for the exam. Apart from that, 3 problem solving questions. These are the essay style writing, like total 45 points. There is 1 5-pointer problem and 2 10-pointer problem. And each of them you need to give proper explanation. How have you came to a result? Final result, of course, is important. Of course, that carries mark, but that does not carry entire marks. It basically, I will definitely look at your explanation, how you reached into that, how you have reached into that result, and that will carry marks basically. One practice midterm quiz is available already. It is 1 attempt to give you a taste of what is coming in your way. It will show you the correct answer, but only once. So basically attempt that if you think you are really prepared yourself. And these practice will be exactly like the midterm environment, like a Respondus lockdown browser, etc., etc., so that you basically get a feel of the midterm, actual midterm coming up on October 19th. Question?
Professor, I have a question. Actually, you put a MIPS instruction links on the quiz, the last quiz, and when I clicked on it, my lockdown browser, locked, and I cannot use it, and I wasted time, and I had a lot of problems like this, and I wasted about 5-7 minutes to find it, or again back it and resume my quiz. So can I print it, the instruction, and put it beside my computer or not?
Yeah, sure. Like I sent an email already this morning. Please check your email. I think there was some link permission issue it's given. I hope I have resolved that. But anyway, if you want to print it upfront and have it available on your desk, you are welcome to do so.
Okay.
And that will be like apart from your one pager page, like that will be separate. Like this one is still, you can have your own note, and it is on top of that. If you want to print one page for the MIPS instruction set, you can do that.
Okay, thank you so much.
Other question? Okay, then let me see what are the topic of interest. Yeah, I believe, yeah, I answered this question already. Okay, there are two. One from, can we review the clock system and memory models and their accompanying question like problem set 1. So, oh no, we have more. Okay, someone just keep on entering. Okay. Okay, this one, and then go over instruction into the machine code like 9 and 12. All right, can we go over constructing of a symbol table for assembly code, how to translate pseudocode into the basic MIP instruction. Okay, can we go to the jump J instruction given PC value? I think this one and this one, quiz 912 question, they are practically the same. Let's go over this first, these two, then I'll come back here, then I'll come back to there. So we have 2 days, like don't worry if we don't cover everything, we have next day to cover. So let me just try this question first. Okay, what was the question? Let me see. Question 9 and 12. Okay, question 9 is this one. Okay, as far as question 9 goes, it is something like this. So you have been given a piece of code and you were asked to machine instruction at the label loop. So this part you need to make. Okay, this part, this B and E, 0 and N, that one you need to answer for, okay, machine code. Okay, generate the machine code for that. Okay, all right. So this one would be, this is the I type instruction, right? First of all, we need to look into the MIPS datasheet for this BNE. BNE is branch or not equal I type. So that means your format is basically opcode RSRT. And then there would be one more information we need to see is this one, your, let's see, there is one more about the BNE, which is, okay, let's see, the BNEs. Okay, branch and not equal. It's basically format is RSRT. Okay, so So we need to see determine the machine code for this instruction, and from this BNE is your RS is this guy. RS is T0 and RT is $0. Okay, now from here, what we need to look at is their register number. 0 is 0, so register number. This is register number 0, and this one is register number T0 is 8. So basically I'm looking into this table. T0 to T7 is 8 to 15 and 0 is 0. So that's your register number 8, and your I type format is this. So it's practically your opcode followed by RS, followed by RT, followed by immediate. Okay, so your opcode, you can get it from here. BNE is 5 hex. So this is opcode is 5 hex. Remember, this is 6-bit. This is 5-bit. This is 5-bit. This is 16-bit. So BNE is 5-bit, and okay, now next part is RS. RS we already retrieved that information, which is 8, and RT is 0. Then the question is, what is this one, right? So this one we calculate like this. Let's say we are computing BNE. Just hold on. Okay. So why this? You just hold on. My browser is frozen. Let's see if it comes back. Okay. All right. So what shall we do? Let's say we are trying to make a machine code for this one, and this one is basically jumping from So it is saying that if the condition meets, then it will go here. So what we'll see, this is first of all, this is a forward jumping. So this immediate value would be a positive value. And what is that value is, what we'll do, we'll basically count the number of instruction till this one from the next to next instruction. Okay, so it is basically with respect to next instruction, I calculate the offset. Okay, so this will be like 1, 2, 3, 4. So this is a plus 4 would be my immediate value. So in that case, so now we have every information to compose the machine code. So opcode is 5 in hex, which is basically your 0, 0, 0, 1, 0, 1, right? It's a 6-bit opcode. That is the opcode for binary for the opcode 6-bit. Then RS is your 8 in a 5-bit. So 0, 1, 0, 0, 0. 4, 5, yeah. And RT is 0, that's easy, 5-bit 0. And my immediate value is 4, positive 4 in a 16-bit term. It is like 0, 0, 0, 0, 2's complement format, 8-bit, 12-bit, 0, 1, 0, 0. Yeah. So now all we need to do is put together this 32-bit together and determine the machine code. So my machine code would be 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, right? And then to write it down in a hex format, what we need to do is basically we group by 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 4. So this is 1, this is 5, 0, 0, 0, 0, 0, 4. So ultimately my machine code will become 0 in a hex 1, 5, 0, 0, 0, 0, 0, 4. Make sense?
So is the order of the machine code the same as this opcode RT immediate?
Order is basically depending on this part, like how the assembler order. This order is assembler provided order, RSRT, right? But this format order is practically machine specific. So RSRT followed the same order as in machine code, but if you actually open the I-type instruction, for example, like this one, let's look at an I-type instruction. Add I. Now see, it is an RTRS. This is from assembler perspective. Assembler treats the first argument as RT, second as RS, and it places, but the machine code format still is the order is the same as in the BNE. So which one is what really depends on this format convention that assembler follows. Assembler follows RT, RS order in the terms of the immediate arithmetic and logic instruction, but for the branch instruction, it follows RS, RT order. So we must be following that as well. Is that, Christopher, is that make sense?
Yes, thank you.
All right, Mike has a question. Doesn't the PC forward jump to J loop? What do you mean, Mike, about that one? Like, can you explain? What do you mean by that?
Never mind. It jumped to end. I got it.
Oh, you got it? Okay, okay, okay. All right. All right. So next one would be the question 10 or 12. It's a jump, right? That's another. So other type of instruction are straightforward, basically. You basically look at the argument and break it down into the opcode and the different fields you have in the in this format, like, and all the binary patterns, put them together, that becomes your machine code. R type is simplest one, except for this shift amount when it comes to the shift. So basically, let's look at the shift one. Shift left logical, right? It says the RD is RT left shifted with the shift amount. That means for this left shift logical and shift right logical, these two instruction, your RS field is going to be 0. So you need to set RS field. You need to set the RS field to 0. So anything is not defined is practically you set it to 0. You need to fill out the RT and RD for that case and shift amount. For other R type instruction like AND, sub, etc., you fill out RS, RT, RD, keep the shift amount bit pattern to all 0, and that way you get your machine code binary for the R type. For the I type, most of the arithmetic and logic functions are straightforward. You basically derive your bit patterns from the opcode and RSRT field and immediate field. Make sure this order of the RSRT is with respect to the what assembler thinks. And the challenging is the BNE be equal to that kind of compare and jump. That instructions are the complicated one. So this is where you need to actually compute the number of instruction offset with respect to the next instruction of that BNE or B equal, etc. And the other one is the J. J instruction machine code is a little bit problematic because it involves the program counter in it. So what you do here,
Professor? Sorry to interrupt you. I just had a quick question. What does goes in the function field in R type instructions?
come again, sorry?
What do we put in function field in R type instructions?
So function code is right there, right? If you look at the R type instruction, this is your opcode, this is your function code. That's what it is. Opcode
All right.
Count.
Okay, thank you.
Okay, so I have one question from Nigwen is that, are you going to provide the order of RSRT on each instruction in the midterm? If it is a special case, yes, I will give probably the BNE, B equal, that sort of thing. By default, you assume it is RT, RS combination. Okay, some opcode RS and RT. Like this one, this is RS, this is RT, sorry, this is RT, this is RS. By default, you assume that. If there is a special case, I will provide it. Or if you have that question, like if it is not provided, you can just call me in and ask me, like if I forgotten that one. Okay. All right, now to the next one is the, let me see, what is that question is. It's kind of given like this. Okay, so for this one, okay, these are the line numbers anyway, 1, 2, 3, 4, just for your easy counting. It says the machine code for line 9, which is J loop. So that means we need to compute the machine code for this guy, J loop. For this one, what we need to do is first of all understand what the J does, right? Let's review it. So J instruction is a program counter equal to jump address. So it sets the program counter to the jump address, and jump address is calculated by this one, right? Jump address is program counter plus 4, and it picks up the 4-bit MSB, and then followed by the address 26-bit field, followed by 20. Okay, so 26-bit plus 20 is 28-bit plus 4-bit from the PC, which is a pseudo-direct addressing. It picks up that and make that target address. So that means we need to start with the target address and what is my current PC, right? So my current PC is this one. This is my PC, and this is my PC plus 4. PC plus 4, right? So that means my PC plus 4 in this case is there anything that quiz says review the following code? Oh, okay. So it starts from this 400800, right? So that means this is at this address. This one is plus 4. So this is plus 0, plus 4, plus 8, plus 12. I'm just putting the address placement plus 14 plus 16, sorry, 16. This is plus 16 plus 20 plus 24. This is plus 28. This is plus 32. Okay, 32. So that means my PC plus 4 is 408000 plus 32 equals, so this address is, this specific address is 00408020. Okay, and we need to jump to the loop, which is this one. So this address, let me just write it down in a different ink, which is 00408008. 408008. Okay, wonderful. So let's write down my PC plus 4-bit pattern here. PC plus 4-bit pattern would be 0000 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 on the 32 bit 4 8 12 16 20 20 24 1 2 3 4 5 6 7 I missed something.
You miss a 0 between 8 and 2.
Ah, right. Thank you. Yes, that's what happened. So that should be 8020, isn't it? Okay. So let's do that. This is 8.
I mean, for the binary code, I think that was correct. The
Oh,
hex
that was
code was
correct.
correct.
Is it? Okay. 00408 020. Okay. Oh, I got it. I got it. Okay. So this one must be 0010 0000. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8. Okay. That's wonderful. And my target program counter or PC next is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay, so where am I? 4, 0, now 8. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, no, that is 1, 0, 0, 0. Right, so this one is, let's check 1, 2, 3, 4, 5, 6, 7, 8. 8 pattern. Now, which part comes as a 26 bits? So, like this part actually comes from this program counter plus 4, and this part is implicitly added by the processor. So here, right, PC plus 4, the highest 4 bit comes from the program counter plus 4, and last 2 bit comes from implicitly added by the processor. So that means my 26 bit pattern is really this guy. That's my jump address. So basically jump loop is your opcode is, let's say, jump opcode is there, 2 hex. So opcode is 2 hex, which means it is like 0 0 0 0 1 0 in a 6 bit. And then the address field, the other part, this address field, we just computed here, right? Address is this. So address field become like 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 0 1 0. To change it to hex, you group from the left side by 4. 4, 4, 4, 4, 4, 4. So it means 0, 8, 1, 0, 2, 0, 0, 2. Okay. seems correct. So I just group them by 4 and have those things converted into the hex representation, digit representation. Question? Nope. Okay. What else? So this is done. Matthew, so your J is also covered up, right? T, you have any further question on this? Other machine code is conversion should be straightforward if we can handle these two, right?
Yes, thank you.
All right. Okay. Now, actually, since we are on this assembly code and all this stuff, why don't we just pick up Christopher's query? Okay, Christopher, is there anything specific that you are looking for, or in general?
Just in general.
Just in general. Okay. Okay. All right. Let's take 5-minute break. About 6:45ish. We'll be back with that discussion. Okay, so over time, let's get back. I see there are some more requests for reviewing.
Professor, can I ask you something?
Yes.
It's related to what you just had done. So when you're given the PC address
Can you
at
speak up
the
a bit more? I can barely.
yes, yes, sorry, is this better?
A little better.
Um, so when you're given the PC address at the jump execution, that's the address. That PC value is what you have to add 4 to begin your process. The PC plus 4, you add it to that value.
Right.
Okay. 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 Thank you.
Okay, so okay, let me stop share screen. Share. Okay, so I have one related from Narinder about this one, quiz number 4. Number 4 seems like related. Yeah, we can. Let's do that first, since we are on the jump instruction anyway. So that quiz is the reverse one of this part, right? That quiz gave you the jump, this 26-bit address already given to you. All right, it gives you the 26-bit address. It gives you the address of the PC plus 4 PC, and basically, and then what you need to do, you need to reconstruct these guys. So it is just the reverse problem of this one, the one that Narinder is asking from quiz 4. So let's try to do that. Okay, so this one is like this. Okay, so it's given that your jump instruction is already having that 26-bit address. So jump, and it's that 26-bit pattern is given to you. It is 3A387, 3A387, 7F8. And your PC is given as 2A89, 2A89, 56B8, 56B8. So what we need to do, first of all, we need to do PC plus 4, which is like a 4 addition on top of that. So that will become like, it doesn't matter, like probably most of the cases will not affect the most significant bits, but who knows, like let's add them. 956 B8, 8 plus 4 is 12, which is C, B, I think C maybe. Maybe CC, let's just cross check that one. Okay, so this one would be 2A 8956 B8 plus 4. Oh, BC. My bad. Okay, BC. This is BC. Okay, BC. Now, you see, like from here, now let's put the bit pattern for the PC plus 4, which is like 0010. A is 10, 1010, 8 is 100, 9 is 1001, 5 is 0101, 6 is 0110, B is 11, which is 1, 011, C is 12, 1100. And now you have to calculate these guys now from here. PC next, which is this 4-bit comes here, 0010, and processor prepends 2 more 0 at the end, and rest 26 bit comes, this 26 bit comes from here. So what is that? So we'll write 3 as 1, okay, so this guy will be like 2-bit, and the rest of them would be 4 bits. So A will be 1, okay, A will be then 1, A is 10, 1010, 30011, 81000, 70111, F is 1111, 8 is 1000. And that is your PC next. Now you just change it to hex by grouping by 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 3, 4. And that will become 2. This is what? 8, 12, 14. 14 is E. 8, 12, this is also 14, which is E, 1, F, E, 0. 2, 8, E, 1, F, E, 0. Yeah. Narinder, is that okay?
Yeah, thank you. Thank you, Professor. Thank you very much.
Professor, could you explain again how you went from PC plus 4 to PC next?
This one? So we basically pick up this one, and then this one, we pick up the 4-bit from the PC, and we add 2 zeros at the LSB side. Then pick up 26-bit from given address pattern, given machine code.
Professor, can we say that like when we are given the PC counter address, is that the address of jump instruction itself?
No, come again. Sorry, I couldn't hear you.
So you know how we are given the PC address in the question?
Yep.
So is that the address of jump instruction?
Yeah, yeah. This is
right.
This is like an immediate part of the jump instruction.
Okay, thank you.
This is the immediate part of the jump instruction.
Okay.
All right. Okay. The next one be okay. So this is done. Now let me come to Christopher's question. This construction of the symbol table. So for that, let's pick up an example from maybe the problem set, which is basically, let's see if we can type in that. So it is in your problem set, problem number 3, 5 to 12, lecture 5 to 12, that problem set number 3. You need to add a symbol table for this program. Oops. Okay. Why is this? Normal, caption, normal. Okay. Okay, all right. So this is big enough. Oops. Actually, I need to. No, not this one. No, this one maybe. Just hold on. Something is new. So this one, right? Control C, Control V, text, Control man. What is this? 10. Oh, this makes sense. Okay, so it's given that you have to make a symbol table out of this program. So what we need to do, we basically need to know where to start this addressing. Okay, where to start this addressing. So for that one, maybe we need to go back to this guy once more. Let's see. So is there anything else? Okay. Oh, okay. So let's say this is given, right? This is given. That means what you need to do if nothing is specified to you. Like in the problem, it was specified what is my startup address for the program, what is my startup address for data. But if nothing is specified, you need to actually go back to this green sheet and consult these addresses. So your program counter, if nothing is given, your program counter starts from this address. So let's assume that in this problem, in this time, to just make a little bit variation from the problem set solution that been given. So we start with, okay, we assume this guy start from your MIPS green sheet provided address 0040 0000. And then we need to determine the addresses for these labels. Main L1, main L2, I think these three, and there are labels of V1 and V2. And data label is strategy is different than the text level or the program levels. So data, for the data, we assume that these guys start from, if nothing is given, these guys start from here, okay? So which is 1 0 0 0 0 0 0 0. That is from the MIPS screen sheet. Okay, now my symbol table, as far as the symbol table is concerned, we have like total 5 symbols to compute, right? Total 5 symbols to compute. These 5 symbols are like this. address. So your symbol entry will be main L1, main L2, and then V1 and V2. All right. So these are the 5 symbols. And now to make our life easy, what we do, we index the instructions in the program. Like these are my instructions and these are my data. These are my data. So I index instructions starting from 0. So this is instruction 0. This is instruction 1. This is 2. This is 3. This is 4. This is 5. This is 6. This is 7. This is 8. Yeah. So that means this is, and let's call this is a power up address or PA. PA is my power up address. For program counter. So simple, what we do is basically PA plus this index multiplied by 4. So these guys' address will be PA main L1. Main L1 is index 6. So it will be 6 multiplied by 4. And this guy will be PA 8 multiplied by 4. So we use calculator, we add these values on top of that, and that becomes basically your, I think this is 00400004. This will be 004000. Wait a minute. 0040, and then it will become like 0018. Let's see. Bring up the calculator.
Professor?
Yes.
For the main, how do you get 00400004 if you're adding 0 times 4?
Oh, thank you very much. Yeah, that's a mistake. So that would be 00.
Oh, okay. Thank you.
Yeah. Okay, so this is 18, 24 is 18, and then 32, right? 32 would be 20 in hex. So this guy will be 00400020. Question so far? All right.
Yes,
Now,
I
yes,
I
yes.
have a question. So if we look at instruction number 0, or I mean the label main, so in that one line we have the symbol and the instruction. Do they take like separate memory addresses in the RAM, or do they take the same?
No, mains are just symbols. Like their purpose is for assemblers to refer in a program to some instruction. So labels are not stored in the memory anywhere in the program memory.
Okay, so only like so if the actual thing that's gonna be stored at 04000 would be the LW command, right? LW instruction.
Machine code for that instruction. Yes.
Yeah. Okay. So okay, thank you.
All right. On the V1 side, so here one important thing is to look at this align. So luckily this dot align is 2 is basically the default alignment. It is your word is divisible by 4 and so on and so forth. So Here challenge is basically to first, what is the initial address? So if your initial address, as I said, like if it is nothing is given, you pick up this guy, okay, from your MIP screen sheet. So first one is straightforward. It is address is that one. It will start from 10000000, right? Now second one is tricky. How we compute that? We practically need to count the bytes here. Practically need to count the bytes here. So for this case, we have how many bytes? 1, 2, 3, 4, 5, blank, 6, 7, 8, 9, 10, 11, 12, and don't forget the null character, 13, right? So there are total 13 bytes. So why this null character is very important? You need to look at this, whether it is given as a .ASCII or as .ASCII. .ASCII directive does not add that additional null, but .ASCII adds the additional null. So you need to be very aware and very mindful about that one. Nonetheless, yes.
Is that the only difference between ASCII Z and ASCII?
Yes.
Okay.
So, so what will happen here is basically now you need to look at, that means your next available address is going to be this address plus 13, which is like something 13, right? But 13 is not divisible by 4, which is needed for a word placement with this alignment 2. So that means we need to go towards the next available address, which is divisible by 2, we divisible by 4 because it's an alignment 2. So that means it will be like 13, 14, 15, 16. Like next is the 16 is divisible by 4. That means you need to add this guy. So this guy plus 16 in base 10. Like this is in base 16, right? And this is in base 10. So that will become, if you calculate that one, that will become like, I think like 1 0 one more, right? So let's see. So you have 1 0 0 0 0 0 0 0 plus 16, which is hex is 1 0 0 0 0 0 1 0. So that's how you basically go for the symbol table construction in from a given program. Question?
Yes, I have a question.
Yes.
So does the align to also, like if we were to load byte after byte, not in a string, but separate data, does it also jump to the next word?
For the byte
Yes.
can be placed at the any address. So alignment 2 means it's basically, it is restricting the placement of the word to a address divisible by 4 and a half word address divisible by 2. And so alignment 1, I believe it does restrict only the half word placement, like is the divisible by 2. And the word is also need to be divisible by 2. And align 0, align 1 not used very frequently. Align 0 means no restriction. It can start from any address, any type, word, half word, byte. It can start from any address.
So it's like the default. Align 2 is like default.
Yeah, align 2 is the default.
So like align 3, like that would not be used then?
Align 3, that's an interesting question. I need to check. Like, why don't you guys also experiment? What does align 3 does? Like, just do a little bit searching and experiment on the Mars. Okay, put it on the discussion question. I'll try to find out. Like, I don't have an answer right away.
Okay, I also had another question about, so I thought that data, like, I guess if you had a label stored at .xturn, I thought that would start at like the 10000 address. So I guess where does xturn start storing labels by default?
Oh, extern. So basically, yeah. So in the case of Mars, okay, let me go back to that one. So this one is like MIPS assumption. Okay, MIPS recommend that you start your placing your data, static data, into this area, like from 100 to 100,800 hex till that address space. That is the MIPS assumption. Now it does not distinguish between an extern or a global or anything like that. It's everything is a static data for in terms of MIPS from the processor side. Now, as an assembler, Mars, it distinguishes between a .extern and a .global to give programmer a little more flexibility and choice where to place the data in. For that case, your extern is starting in this whole address, right? And please look at those corresponding slides. So it will be somewhat here and covering this part, and after that the static data start get populated, and for it I think it starts from 100,100,000. It's all started from that for the Mars by default. But this is but if the problem doesn't give you any hint as such, you assume this memory alignment suggestion. Make sense?
Okay, yeah.
Okay, so let me stop here. Christopher, is that symbol table generation make sense to you?
Yeah, perfect. Thank you.
Okay, so so we have Carter's question. So let us come back next day on this one. Let me start with that one first, and then we can go over this one. I hope we have the board work for that one already. Oh yeah, so I can reuse that one for Michael's question there. Yeah, and please keep on adding more if you need to discuss. So I will address Carter first next day, and then we'll go with the Michael. Other things I believe we are done. All right, thank you very much, and we'll all see